Maria Kuptsova is an artist, architect, and researcher. Maria's PhD research at IAAC points towards the possibility of developing a bio-machinic design technique with an aim to impart biological intelligence into inorganic objects and synthetic environments. This investigation is carried forward through her independent artistic projects, architectural practice in collaboration with ecoLogicStudio in London, as well as research and academic experience at the University of Innsbruck, the Institute for Advanced Architecture of Catalonia, the Bartlett School of Architecture, and the digital Future Colloquium, among other institutions.
Hi, hola, ¿qué tal? Well, I speak a little bit of Spanish, but it's definitely not enough to run the presentation in Spanish or Portuguese, so I will keep the English. And it's really good to be here. Really beautiful place and beautiful community that we have here. It's the first time for me in Uruguay, first time in this continent. Do you hear me like this when I'm speaking? Yeah. Super. So, beautiful talk we had today in the morning of Neil Lichner. So I was thinking I will reflect on the... I think we can switch off the light for the better. I was thinking that if Neil has been talking about acceleration of AI, I will slow down a little bit and I will talk about the velocity of ecological processes. And through this journey of 1 hour, I will try to be short, I will drive you through some project that I do independently as my practice, as well as research associated at the Synthetic Landscape Lab of the University of Innsbruck. I will show you also some beautiful work of my genius students at the University of Innsbruck, and as well as some collaborations that I do with my friends as an artistic practice. So again, talking about the velocity of ecological processes, we are questioning how contemporary technology could follow the fluxes of natural systems in different scales. How does the velocity of accelerated machinery that Neil has been talking today in the morning and technology coincide with ecological rhythms? With the proliferation of new biodigital agency, how can we create more inclusive design systems that are better to meet the needs of diverse range of entities and establish new types of relationships with the environment? Some beautiful image that I really love from as mapping that I've been taking some years back. These processes which are being regulated by other intelligences, Neil called them alien, other rather than human. But I'm talking not only about the machinic algorithms, non-human agencies as transgenic plants, planetary viruses that we just had recently, are equal actors within the hybrid reality we live in today. The behavioral model of fungus, bacteria, insects, and animals can be also understood as a form of intelligence. New computational powers now involve both technological and natural systems in the process. And that's the processes that I engage in my practice. Design in this case is a biotechnological apparatus, an extended cognitive structure that incorporates various forms of intelligence, including human, artificial, and biological. In my practice, I explore in depth the possibility of design as a collaborative system between different forms of intelligence, focusing primarily on the possibility of embedding biological behaviors into the artificial systems. I'm running you through the very beautiful project, the imagery of our master project at the Synthetic Landscape Lab by Charles Burian. We are studying and seeing how could we control and navigate the growth of the mycelium system within the scaffold structure, as well as use the potential of mycelium as a metabolization system for the waste products. Or another project by Stefan Fuchs, another master student at the Synthetic Landscape Lab, where we explore the intelligence of the swarm behavior of bee organism, using artificial scaffolds, manipulating its formation through the levels of control. The organism of bees is a design method. Human design takes place here as a creation or mediation of processes through the gradients of control. No, it's a video, I think it should run.
Yeah, it was running.
Was it?
Yes.
Okay, beautiful beast. In 1980s, Félix Guattari and Gilles Deleuze rejected traditional dualistic notions that strictly separate humans from non-human entities. They argue for more complex understanding of reality, emphasizing the interconnectedness and interdependence of all entities. They propose a vision of the world as a rhizomatic structure, where connections between elements are non-linear and constantly changing. In their framework, the non-human is not seen as passive object, but as an active participant in the formation of assemblages. They recognize the agency and creativity of non-human entities, including animals, machines, and natural forces. The non-human is considered as having its own unique contributions, trajectories, and potential for the transformation. Today, we are exactly in the moment when ambiguous, systemic, and intelligent technologies are opening the doors of the laboratories and basically running out into our cities. They become an equal actor in the ecosystem in which we live, a part of the landscape choreography. Technology embedded in multiple objects within the landscape allow new regimes and metabolism to evolve. And that might become scary, as Neil was mentioning in the morning, if we don't consider ecological element as an integral part of these processes. And vice versa, we need to realize that ecology includes technological systems. Our ecosystem is a natural technical continuum. But the good point that we are actually now starting to have an access to other intelligences. Like, we could co-design with them, and we could embed them in the design process by the means of intelligent technologies. We are capable to track the micro-impulses of plants, understand the languages of plants and fungi that I'll drive a little bit further on. Do you have the sound? Okay, doesn't matter. There is actually the project consists of the sound generation. Fortunately, it doesn't work here, but it doesn't matter. So this concept we study in detail with my friend Sergei Kostevka. It's in a cyborganic sound installation which is called Pine Drone. One of the distinctive features of living tissue is the ability to generate bioelectrical potential, which are involved in the regulation of cellular processes, as well as being responsible for the transfer of information from various organs and tissues of living organisms. The mechanism allows an animal or plant to respond to external influences by generating bioelectrical impulses. By measuring the gradients of the bioelectric potential based on a non-invasive method where electrodes are placed on the surface of the plant, biological agent as you see here. We transmit the data for processing by a microcomputer, an artificial agent. From acquiring data, the behavior of artificial agent is determined and manifested by generation of sound code that depends on the behavior of biological agent. While transmitting information within a system, biological agents can influence each other and change its behavior. In turn, by analyzing the electrical potential, these kinds of changes can be monitored and broadcasted into the sound form. So this project we've been developing, so we're collecting the data from the biological species and transforming it into the sound code. And this is actually a rehearsal for one of the festivals on the coast of the Baltic Sea. So can you imagine there was a huge rave where everybody was partying and there was the DJs. And Mr. Gaby came and said, okay, we will have also a rave, but it will be a rave of a pine. So the pine drone is basically a pine. It's playing a drone. And we had a great group of people coming to us after all the other stages, being a little bit high, but enjoying and actually finding the unity with these processes. Unfortunately, I didn't run here now the sound, because the video of the sound is actually the generated compositions, but you can just maybe check it online on my webpage and listen to it in a calmer atmosphere. If we look at the microscopic pattern of food, we can see the enormous level of complexity embedded in the structure. It contains information about intelligent mechanisms of photosynthesis, growth, water, and food distribution. Fibers give mechanical support. Parenchyma transports and stores food. Vessels transport water. What incredible capabilities that wood has in its living state, no? Anisotrophic properties are the most important characteristics of wood structure, which represents its constant interaction with the environment. These qualities, which are usually considered as negative side effects, especially in architecture and construction, can be reinterpreted and reused in the design of artificial living systems, capable of interacting with the environment. I explore design scenarios in which data about biological material is extracted from a living system, processed by machinic algorithms, and reintegrated into synthetic matter in my research project Arbor, proposing a new cyborganic cycle of wood. And this research is actually the start of my PhD that I'm running at the Synthetic Landscape Lab under the supervision of Professor Claudia Pasquera. While architectural materials has been traditionally classified as structural or functional and viewed as a characteristics of form rather than generating factor, in natural systems it's difficult to distinguish between structural and functional materials. Biological matter is heterogeneous and informed through the direct connection with the environment. Form embodies material intelligence and structure through bottom-up processes. Wood is widely used in architectural construction because of its mechanical, environmental, economical, acoustical, elastic, thermal, aesthetical properties. However, the heterogeneous properties that I was mentioning before, possessed by wood in its living state, are usually considered rather problematic. The idea to learn the intelligence of an organic structure and inform computational process with the knowledge struck me at the very beginning of my research and pushed me further. To study the material organization of wood, I used a large data set on the botanical characteristics of different wooden species developed by the Archiwood projects. Micro-images of about 1,000 wooden species were collected and analyzed by the botanists with different contrasting techniques. I need to hear the underline that it has been very difficult part to find a data set for this research. I use generative adversarial networks as a method for extracting material organization principles from an existing data set of timber structure for its further implementation in the volumetric models. The organic data here informs inorganic computational system with its own evolutionary neural network algorithm. The potential for artificial intelligence is used as a tool that amplifies knowledge, enabling the detection of characteristics, patterns, and relationships across the vast amount of data which wouldn't be accessible to human otherwise. For each wood species, there are 3 anatomical cuts associated with 3 planes of symmetry, radial, tangential, and longitude. I never can pronounce this word. Taking in 3 magnifications of the microscope, and then running you through some of the research that I've done in this part. A set of experiments was held in all the section cuts and magnification lenses, and the transverse cut in magnification 200 has been selected as the most consistent, and this research I'm dragging further in my exploration. Come on. Okay, here we have. We know that conceptually, GAN consists of 2 neural networks which work together. Neil was also talking in the morning today, discriminator and generator. The generator produces images that look like given example, and the discriminator compares the generated images with the originals and updates the generator if it succeeds. Such cooperation not only allows 2 networks to teach each other, but also to understand the main principles and pattern of given data. This leads to the main advantage of GAN, which is ability to generate new unseen imagery based on provided examples, what allows such networks to interpolate between selected pairs of images by generating intermediate steps. During the training process, GAN architecture forms a latent space. The latent vector interpolation, translation into z-axis of volumetric structure, is used as a method to visualize the internal and external morphology of timber material organization. The latent vector for visceral neural network is translated into z-axis of volumetric model. In this process, the basic geometric data describing the anatomical properties of timber structure as a point cloud is extracted. This network of points describes distribution of material as behavioral pattern. It rethinks the concept of growth, recalling the growth patterns and ratios of biological systems. Proximity algorithm is used as a method to evaluate the density of the point cloud, which would be optimal for the fabrication process, however, would still keep the complexity and the density of biological matter. These discontinuous volumetric datasets translate the material organization principles of wood through the gradients of digital fiber densities. Again, through the set experiment, I come to the most successful that I use for my further exploration. This method aims to replace digital form finding based on form optimization to potential programming of form through the distribution of material within the design object. This step we could also see as a potential generation of machinic movement or the path for material deposition. Avoiding the modeling process could be an option here, and the distribution of point and distribution of the fibers could be basically generating a tool path for the machine to deposit the material, basically following the process of bitmap printing. But that's not my step that I go as the next step. In order to relate this point cloud to the synthetic material system, each point of the point cloud is equalized to a voxel with specific volume and weight. Now, every digital voxel could be translated into the voxel of physical matter, synthetic wooden material. Revealing the memory of each section cut of a tree, the material becomes an augmented library of knowledge from different tree species, presented in one sculpture. This knowledge is still limited to the available data sets and archives, obviously. In case we have larger data sets on the characteristics of specific wooden types, we could start tracing the relationships of the very specific species of a wooden type with its environment, compare and analyze its patterns, morphological complexity, performative aspects, and of course design would reflect this into projected directly into its systems. And here, maybe coming back to the discussion that we had in the morning about the limitation of the data sets we currently have nowadays. But I think the contribution also of this design method or design method of this kind to the field is consisting also of pushing the existing boundary of scientific knowledge and opening new steps for botanical exploration of different wooden species. And actually, back in 2019, I've been starting this research for quite a bit of time already, like before the COVID. I think that was this project before the COVID. And some years later, I found several research papers how the botanists are using very similar methods in order to identify different wooden species. So basically, as a next step after this research, there has been a lot of explorations in the botanical field as well, using similar methods. Through the vertical evolution of volumetric structure, following the transverse section cut as I was showing you before, we could also recognize a pattern of wood in tangential sectioning. And this, I think, is very beautiful now, so that the section cut that I'm using for the generation of my vertical morphology are starting to recall in tangential cut the wooden system. So we could be working on the combination of two informational data sets. The material pillow aims to grow vertically, recalling the idea of a tree, a traditional archetype of an architectural column. the morphological explorations follows the logic of material distribution, learning the complexity of ecological system. Each point in the section of the synthetic object, and you see here the section through the object, will be equalized with a particle of wood, which comes from the living tree and keeps its ability to store the carbon. By calculating the density of the point cloud in each section cut, we could approximate the amount of carbon captured by the tree and stored in the voxel of the synthetic structure. Measuring the full biomass of the voxelized point cloud, we could estimate its carbon capturing potential. Multiplying this amount by 3.67, you have this number in the corner, we will receive the amount of carbon dioxide which was captured by the tree in its living state. Looking to the distribution of densities, we can map the intensities of carbon within the structure as a gradient field. To evaluate the carbon potential of the trees in the natural ecosystem, we use leader scanning, which allows to measure the biomass of the tree. 15% of the biomass of the tree would be carbon, which is stored in its structure. That would mean that in its living state, the tree would remetabolize 3 times more of carbon dioxide to this number. So, releasing the oxygen to the atmosphere, it decomposes CO2 and keeps the carbon stored in its structure. The forest capacity to capture CO2 is different in elevation. This diversity in carbon capturing is nuanced by differences in biomass distribution through the branches, leaves, trunks, and other arboreal parts. To translate this resulting data back into matter, the wooden-based material system has been investigated in a series of experiments. These studies present a new regenerative life cycle of matter from wood in its living state to recycled wooden-based material, which becomes another step in the remetabolization process. 3 different material systems have been developed and tested for its carbon capturing potential. First experiment has been focused on the development of water-based material system using recycled wood powder and agar or chitosan in some other cases as the main ingredients of the printing paste. I'm going to drag you through the video which presents the whole process. So for this test, the material has been collected from a local wooden industry in Tyrol. In this production chain, the wooden chips and sawdust is basically just a waste product which is getting rotten and emits a large amount of methane. So I propose to look a little bit different into this problem and look at this as a basically potential free material, fully ecological for 3D print. You've been just watching the process of the preparation of the printing paste. Here we are designing a custom-made extruder, which is basically we're starting just with a simple syringe and then starting to control the temperatures, the deposition rates, and designing the material workflow, which is basically taking into account the material viscosity, extrusion pressure, and deposition rate. And through the years of experiment, we actually came up with some successful results, which allowing me to print a material pile of 40 by 40 by 40, and which is a limitation of my current custom-made 3D printing machine. And of course, it would be very important to bring into this research different types of wood. Now I'm using the mixed wooden chips. And then if we kind of recall the previous steps when I'm collecting the material data from the different wooden species, how there would be definitely a reflection if we use the same type of wooden chips in the printing process and see how does the structure or the deposition would be affected. This wooden-based material is entirely organic, which is obviously provokes a lot of growth. And I'm exploring how does the mycelium is starting to come into the relationship with the wooden cheese. And this exploration, I look in my next experiments, which actually gave me another branch for the project Hive, but I think it's still very relevant for the previous research I've been showing to you. So we're thinking the relationship between the wood and the mycelium. The Hive project proposed the the use of the mycelium, fungal mycelium, as a structural and performative layer of a design piece. First experiments were focusing on molding the voxels of physical material, which could be equalized to the volume of digital voxel that you saw in the previous imagery. During the fabrication of wooden paste pink oyster, Lithorus jamus, with additional nutritional ingredients are planted into the structure. Sprucing the walls of the sculpture, the mycelium compacts the wood with its nets and creates its own microenvironment. The synthetic materiality remembers the tactility and smell of a living matter, which is very beautiful, integrating them into the new form of relationships. Fungal body is a living entity inhabiting the structure, which plays a role in metabolism of the whole system. Increasing, of course, the carbon capturing capacity of the synthetic material, because here we know that fungal mycelium would also be capable to store the carbon. As a next step of material exploration, I focus on the 3D printing using the wooden sawdust. I use also the sawdust as a fill material, which would help me to 3D print, as well as would serve as a nutritious environment for the mycelium printing. This research allows to go from molding to 3D printing, providing sufficient body of 3D printed structure for the growth of mycelium fibers, which was a great problem for me in the initial steps of the research. Spreading within the 3D printed piece, mycelium penetrates its folds, giving another level of resistance to the structure, as well as preventing the shrinkage during the drying process. The potential of this system for structural stability, as well as enhancing fire resistance, still should be explored in the next experiments. Spreading throughout the 3D printed piece, fungi also serve as bioindicator, capable to monitor the presence of toxins and other pollutants in the environment. In the study, Dashibi and Adamatsky investigate the actinic potential of oyster mushroom, which is measured in the form of spikes of electrical activity. The complexity of the spikes frames a fungal meta-language, which can be measured and decoded. Considering the ability of the mushroom mycelium to solve a wide range of computational tasks, we can imagine a use of fungi properties as a biosensor, which is capable of receiving and transmitting information from a design piece to potentially an automated system for their production. Same as a natural system, trees and fungi have mutualistic relationships. The fungus grows a network of hyphae around the roots of the tree, increasing the tree's ability to absorb water and nutrients from the soil, allowing for the exchange of resources and information between plants, connects individual plants together to transfer water, nitrogen, carbon, and other minerals. This biotechnological apparatus would set another system of relationship with the environment, programming the relationship with the ecosystem by the means of biological agency. Extracted from living system and processed with machine learning algorithms, information is fed back into matter in the process of fabrication or gardening. Predictive models here using machine learning are well suited to understand the behavior of materials and biological systems. In collaboration with living systems, they will have the potential to deliver prompt feedback for design and fabrication processes. enabling the anticipation of material transformations during fabrication and development of adaptive manufacturing strategies that consider the heterogeneity of material and capacity of biological system to be cognitive and metabolical pattern of the landscape. I really love what you do. The speed of 3D printing is informed by the growth ratio of fungi mycelium, integrating biological timeframes into built environment. The design piece is grown by a metabolic process, evolving over time. This is challenging the idea of design as an act taking place before completion, handover, and habitation instead of building new bridges of what it means to inhabit and live a living architecture. I'm quoting Thompson and Tonke. To fully harness the potential of bio-based and living materials, we would need to develop a biotechnological apparatus that understands the life cycles, growth decay ratios, and variability of bio and living matter, not as failures, but as active design parameters. Developing protocols and tools for recording, characterizing, and predicting organismal life activity, the digital algorithm will not be only informed, but also possibly controlled by a living system. Mycelium will become an active design agency, or we could imagine that, uses machine learning as a tool to receive, process, and respond to its needs and senses. Although such a system will be designed by humans, further development in the field of computer-plant interaction might create a space for technological input from non-human organisms themselves. As well, would allow a more detailed study of the intelligence of biological system and its potential as active design agency. I hope you're not tired of all these experiments. We good? See how we are timing. So here comes the third experiment. This one will be quick. So the third experiment I'm conducting with a prefabricated wooden-based PLA material designed by extruder company, where at the time my friend has been actually in charge of the production process. And here we are using almost 30% of wood, which is still binded with the 60% of PLA material. The use of a large-scale industrial 3D printer RASP allows the material experimentation at the larger scale. And even though amount of wood is equal to 40%, the potential for carbon harvesting of this material is quite high still. To test the material system on larger scale, a component system has been developed and framed into the cyborganic sculpture that has been a part of a potentiality exhibition in Innsbruck. Arbor is a biotechnological vision of a tree, which presents the possibility of its organic growth by the means of technologies. It's a new kind of living object which changes understanding of design, introducing regenerative life cycles of matter. Here are some shots from the exhibition. And my beautiful PhD advisor, Dr. Pratt. We are running. So this type of, I call them cyborganic, so they are cybernetic and organic at the same time. Cyborganic prototypes can be considered as living entities, which is integrating biological and technological aspects in its fabrication, computation, and maintaining protocols, which could be potentially artificially grown in the city. They examine the life cycle of wood from tree grown or from tree in its living state to the point at which wood products become waste generated during construction and demolition activities. Arbor is a vertical system which is exploring the idea of architectural column. Possible bifurcation of the system is investigated through a set of curated visual experiments. I will just refill my water. And I think it should be a video. So from, as you see again, from the biological particles to digital point clouds, from point to voxel, from voxel back into the matter, this type of system develops sustainable cycles of matter to be contextualized in a new formal articulation, with an aim to impart biological intelligence into inorganic objects and synthetic environments. So then how we engage with this landscape? We call this pure nature, which is not exactly true. This landscape is being fully controlled by human, and we see traces of human activity which I'm studying under the satellite imagery. And this is one of the places in Canada, which is also under study by the project of Edward Butinsky in his project Manufactured Landscapes. So how could we, change the vision of this productive landscape, introducing new metabolic processes and cycles of matter? I think this is the question that I'm, of course, being triggered by all this research. Can we think about the velocity of the development of this landscape, the velocity which would take into account ecological agency? Forests are critical in addressing the climate crisis. Second to the ocean, forests and forest products capture almost 15% of our global carbon emissions each year. Would it be possible to learn from that? To explore that we, in a larger scale, we use the same computational protocol as I've been presenting in my previous project with my colleagues Vadim Smachty and Artem Konevskih in the workshop we run in Bartlett School of Architecture. Together with the students, we were envisioning the landscape of carbon storage, which form a complex multi-layered system, learning information from the satellites, reading, using same machine learning-based design techniques. Students were exploring the capability of the synthetic landscape to metabolize pollution. These volumetric explorations are proposing different processes rather than currently present in our planet. I think I'm getting quite late on time for all the chapters that I wanted to show you, but I still wanted to show you one project which addresses the same question of the pollution. Unfortunately, again, I don't have a sound here, which is beautiful, also recording of the information from the process. I'm introducing you the process, the project Regeneration. It's a research project which I ran with my colleague Marina Muzica in last summer. It has been developed for one of the festivals. This project investigates the state of our urban sphere by decoding data on the pollution of local water sources into the form of synthetic sculptures. Questioning the aesthetics, how do they form by the processes which are definitely not ideal, which is happening in our environment. I think it's quite interesting to look, I put this video at the beginning so you could see this dystopic scenario of our project development in a large tanks of water. But I would maybe run you through the process. So, introducing both digital and material forms of computation, the project searches for new forms and aesthetics programmed by digital, chemical, and biological processes. The synthetic sculptures are based on the Wolf-Hilbert's bio-rock technology, developed to restore coral reefs in marine life. This technology allows crystal structure to grow over the metal substrate, stimulated by the process of electrolysis, so it's a process of electroaccumulation of minerals. This is basically by passing the electric current through a metal substrate placed in a volume of water. Yes, sorry. In the experiments, Wolf-Hilberts used the electrical accumulation of minerals for the restoration of coral reefs, but our project bases this research on the experiments with an aim to allow the matter to program the form of an art piece. A series of investigation, actually I'm running you through the investigation that we had been doing previously with master students Miro Ivan, and which became the input for the further explorations. So a series of experimentation has been followed by us to get a control of the accumulation process and basically devise a physical system which can be by computation manipulated to suit our specific purpose. By establishing a low voltage current between electrodes in seawater, calcium carbonates, magnesium hydroxide, and hydrogen are precipitated at the cathode, a positive charge, while the anode, a negative charge, produce oxygen and chlorine. So that's basically the main process which is happening. These experiments with calcium and phosphates have demonstrated the feasibility of targeting mineral pollution seawater to create the required mineralized building material that we are using for the construction of our sculptures. The spatial learning system is based on the study of water composition of local sources, with samples taken from the Baltic Sea. The morphology, resolution, color, and porosity of the art object are directly programmed by the chemical composition of water. In order to drive the morphology, we've been passing through the very interesting experiments. So we've been, beside the collecting of water from local sources, we've been collecting the metal waste, which is basically accumulated on the bottom of all our oceans and rivers in the megapolises. And this data set is just some artifacts that we have found. Again, I'm passing through the same process of the style gun in order to start generating the morphology, which will inform the further exploration of the sculptural systems. Quickly running through the computational model and the iterations of the different sculptures which are using the fiber system. And maybe here we'll go very quickly because it's just instruction for the bending machine to bend the metal structure. So some processes that you already saw in the video. And each object is unique, created in the interaction with environment. And it's also becoming the identifier of ecological conditions of particular location. The chemicals and metals present in the aquatic ecosystem create the aesthetics of the project, converting physical particles into the digital bits of code. The aesthetic form becomes an identifier of pollution present in the water ecosystem. The synthetic sculpture, as I was already saying, presents a different kind of aesthetic. Not an ideal beauty that we would probably envision, but one created by destructive processes going in our world. Their aesthetic form embodies ecological agency. The level of classification of the minerals acts almost as indicator of the pollution level in the local marine environment. From mineral accumulation, that we study also under the microscope, to the synthetic crystallization. Of course, the crystallization is another process, a material process that we are fascinated about with my colleagues. So approaching it both as an analog model using salt crystals or electroaccumulation of minerals as a method to compute form. And engaging also directly with ice crystal with an aim to engage with the landscape using snow and ice as potential building material. We are located in Alps, in Innsbruck. And of course, when you come to Alps, the most striking phenomenon that you see, first of all, is melting glaciers. And the loss of ice body reveals the past of the history of our planet, and this is fascinating. How does we could decode the past through the composition of the particles. And you know that the scientists are extracting the cores from the body of the glaciers in order to study what has been present thousands of years before they have been present on the planet. And basically we are losing this information and we cannot do much, but we still forced to give our approach to this. So some imagery that I'm running here is the exploration by our students at the Synthetic Landscape Lab, where we look at the glaciers as basically a massive storage of analog data. which we are losing in time. And the question is how we engage with these processes now. The problem should be approached anyhow. And in the lab we speculate in the scenarios which use local processes and resources as a building block for the future projects. I know the projects now are bringing a little bit of cold. Here it's a little bit even colder, but this is the whole year looks like that now. So within this conceptual framework, the project Drone Ecologies that we've been running also some years back in the Synthetic Landscape Lab, proposing a spatial learning system which enhances human-landscape interaction through machinic protocols. We study how could we engage with alpine landscape, again through the level of controls, introducing machinic agency as mediator between human and the environment. The project explores the behavior of self-organizing multi-agent organizations to simultaneously read and decode the winter landscape, using snow and ice as construction material. It aims at creating a temporal, dynamic architecture, proposing new ways of reading, exploring, and interacting with otherwise inaccessible landscape of the glacier. Intelligent mechanical agents are no longer a mechanism in the Cartesian sense. They take part in the milieu by playing the role of perception organs, like scanning and monitoring, organs of analysis based on calculating for existing data, and organs of synthesis. As a form of machinic agents, act on site in a systematic way, constantly interacting with an organic form, with the landscape. The organic form does not just give form as such, but also organizes matter conditioned by recursive algorithm, environmental conditions, and crystallization process, which computes material formation. Two different types of machinic agents are employed to autonomously execute different tasks: aerial surveying and aerial material deposition. Human agents become inherent part of synthetic landscape development through the complex system of relationship with organic matter and machinic agents. The drone flies every single trajectory several times, accumulating multiple layers of snow. While drones employ for material deposition continue, and they continue to transform and recode existing landscape following the flow path which you see here in the image. The whole process is repeated and repeated over again. So in this process, what triggers me that the design logic becomes an emergent property of a cybernetic process or conversation or relationship with the landscape. The mathematical landscape is formed as a result of organic mechanical operations, an outcome of collaborative design process between organic form, environmental factors, material programming, mechanical and human agents. With ideas such as data analysis, machine learning, material programming, biofabrication, design processes are fully automized. And that such an automatization is aiming to be ecological and sustainable, which implies the realization of complex cybernetic systems. The landscape turns to be constantly changing biosynthetic ecosystem, where machine, biological, and human agents are paired in their actions towards the landscape. New material life cycle and metabolism of the landscape is defined by a system of interaction between biological, human, and machinic agents. The velocity of the landscape development follows the speed of ecological system. And here I would like to conclude. Thank you very much.